Welcome to Mr. Hamilton's Math Bites. So far we've looked at 2 rules to define sequences, and now we're going to look at 3 more in this second part. Our third example is fractions. Given the following sequence, and what we want to do is we want to determine some type of recursive formula, or even better, a general term. Specifically going to ask us here to find a general term. Remember, a general term is a term that I can find the value directly without substituting all the previous ones into that equation. So we're given this sequence, and so the key for this is we want to look at the numerators and denominators separately. And then what we're going to do is the things in the numerator we're going to label with the term nn instead of tn, and in the denominator we're going to label with the term dn instead of tn, just to keep those separate. The first thing we want to do is, as always, see if it's arithmetic or geometric. And then there are some other things we need to recognize. And if we see a pattern 1, 4, 9, 16, 25, etc., that's an n squared pattern because all those values are squared. And if we see a pattern that's going 1, 8, 27, 64, 125, that's an n cubed pattern. And that's because this term is 1 cubed, that's because this term is 2 cubed, it's because this term is 3 cubed, etc. So let's look at these separately here. I'm going to look at the numerator on the left, and I'm going to look at the denominator on the right. The numerator is 3, 5, 7, 9, 11, 13, etc. And so that's pretty clear that the difference between each one of those is 2. So this is an arithmetic sequence. It's a common difference of 2. And we know that if that wasn't obvious to us, we could take the later value, subtract the previous one. So 5 minus 3 is 2, 7 minus 5 is 2, etc. And so once we know that, we see the starting value is 3. The common difference, the d value, is 2. And the general term for an arithmetic sequence is found by a plus n minus 1 times d. There's your a value, your d value, and so we can simplify this to say that nn is equal to 3 plus, and I use the distributive property, so I'm going to get 2n minus 2, and now I'm going to combine the like terms on the right side. 3 minus 2 is 1, so 1 plus 2n, which generally we write the value of the variable first, so we can write that as 2n plus 1. Now that is true for all natural numbers. Let's look at the denominators now. 4, 9, 16, 25, 36, 49, etc. Now we know that those are squares. We see that up above. The problem is this doesn't start at 1. Alright? It's not arithmetic and geometric. We'll note very quickly as well, but we see those are squares. And so what we want to do here is we want to say, alright, well, if the n term is, if the term number is the following, and the term values are a little bit off, then what do I actually have here? I've got 4, 9, 16, 25, 36, etc. Then if we write this in terms of n, what I'm going to do here is I'm going to write it as if it was a square. So I'm going to write it as though it were 1 squared. But what do I have to add to that 1 before squaring it? I have to add 1. And then in the second case, if this was 2 squared, well, that would be 4, but it's the next value squared up. So it's 3 squared. Well, that's 2 plus 1 all squared. The next one is 4 squared. Well, that's 1 more than 3. The next one is 5 squared, which is 1 more than 4. And the next one is 6 squared, which is 1 more than 5. So what you've done in every case is you've taken the numbers 1, 2, 3, 4, and 5. You're adding 1 to each of those terms before squaring it in order to get the squared values, but 1 earlier than you would expect. So what that gives us is the denominator terms are going to be n plus 1 all squared, such that n again is a set of all natural numbers. And then you put those two together. I'm going to do that below. We combine the numerator and denominator to get a single general term. So Tn is equal to Nn over Dn. Well, I'll just sub those in. 2n plus 1 over n plus 1 all squared, where n is a set of all natural numbers. And there you go. There's your final general term for that sequence. That is probably going to be the most complicated situation, because not only are you going to have to figure out the numerator but also the denominator and then put them all back together at the end. Now there are two questions that still arise and that we see from time to time in what we'll investigate in this course, and that is if a number is repeated but seems to get one place bigger every time. So we move 2 from 2 to 22 to tens, from tens to hundreds to 222 to thousands, 2,222, etc. And regardless of what the number is, if it's anything between 1 and 9, it's going to do the same thing from the same equation. And so this is the equation that we can use. I'm not going to derive why this works, but I'm going to just show you why this works quickly. If we have T1, in the case of 2 and 222 and 222, etc., then I'm going to go 2 over 9, because b is the repeated number, 10 to the power of 1 minus 1. And what we get is 2 over 9 times 10 to the power of 1, which is 10 minus 1, which is 9. And so the 9 and the 9 cancel out, leaving us with 2. If you check the second term, again, 2 over 9 times 10 to the power of 2 minus 1. I get 2 over 9 times 100 minus 1, which is 99. And 99 divided by 9 is simply 11. 2 times 11 is going to give me 22. Again, let's do it for the third term and see how this is working. 2 to the power of, or 2 over 9 times 10 to the power of 3 minus 1. And so what you get here is 2 over 9 times 999, which is canceling out to give us 2 times 111. And so what you're going to do is you're going to get it multiplied by 1, by 111, by 11, by 111, by 1,111, etc. So by multiplying by all those digits of 1, you simply get the same number but moved over one bigger as far as the tens, hundreds, thousands are concerned. And that would work for anything. So for example, if you wanted to quickly try 777, 777, your general term would be t to the n equals 7 over 9 times 10 to the power of n minus 1. The last example I told you I was going to go over is an example that comes into play when the sign is changing. And this we'll see a little bit. Don't let it trick you. It's not that confusing if you can see what's happening. It's changing signs, not charging signs, changing signs. And so if we have negative 1 followed by 2, followed by negative 3, followed by 4, followed by negative 5, what that is it's simply t to the n is equal to negative 1 to some power. Because it starts at a power that's negative, we simply say that it's to the power of n times the nth term. So that the first one now, this becomes negative 1 to the power of 1, which is negative 1, times 1. Negative 1 times 1 is negative 1. The second term, negative 1 to the power of 2, which is positive 1, times 2, and you get positive 2. Now, if instead the situation was 1, negative 2, 3, negative 4, 5, etc., think for a second what it would be. We end up getting is negative 1, but you can't multiply it to the nth, because if you put it to the power of n, and the first term is n, then you're going to get a negative 1 to the power of 1 is going to make it negative. So we either have to go plus 1 or minus 1 in that exponent in order for that to happen. In this case, we could write n plus 1 on the exponent. And there you go. There are some good tools, 5 good tools, as we'll come up with various situations for finding recursive formulas, finding general terms, and finding patterns for various sequences.